Introducing stereochemistry introduces new terms for isomers. So let's review. Isomers are compounds with the same formula but different structures. There are constitutional isomers where the bonding is changed, or stereoisomers, which differ in the spatial arrangement of atoms. Stereoisomers can be further broken down into enantiomers, which are stereoisomers that are mirror images of one another, or diastereomers, which are stereoisomers that are not mirror images of one another. A good rule of thumb to keep this straight a little bit, diastereomers require two stereocenters. So let's give you an example here. We have this trans alkene from before, and we have this cis alkene. These each have two stereocenters, and they're not mirror images of one another. So these two are going to be diastereomers. Let's take another example. If we have these two chloro compounds, one of them is a dash, the other one is a wedge. There's only one stereocenter here, and because these are mirror images of each other, they're going to be enantiomers. Another way to tell if something is an enantiomer is to assign the stereochemistry. In this case, this is 1, 2, 3, which would be clockwise, but the chlorine is in the wrong direction, so this is S. 1, 2, 3, again clockwise, this is R. If all of the stereocenters are exactly opposite, then the two compounds will be enantiomers. So let's look at an example where we have two stereocenters in a compound. If we are comparing these two compounds, you should notice that we go from a dash to a wedge, but from a wedge to a wedge. So what has happened here is these compounds are no longer mirror images of each other. They are chiral, but because only one of the stereocenters changed, these two will be diastereomers. We could do the same system where we actually assign the stereochemistry. So for this chlorine, this will be S. For this stereocenter here, this is 1, 2, 3, that'll be R. So we go from an SR to, again, this OH didn't change, so that'll be an R, and RR. So we have SR versus RR. Only one of them changed in this case. So these will be diastereomers. Let's take a look at this example. Here, both stereocenters went from being a dash to a wedge. So even though there are two stereocenters in each compound, these are still mirror images. These are enantiomers. So let's take a look at a more complicated example. We have all four stereoisomers of this 1,3-dimethyl cyclohexane. We have two cis forms and two trans forms. So now we're trying to figure out the relationship between each of these to each other. The first thing that you should notice, if we compare these two, these are actually the same. These are meso. Why are they meso? Even though they both have two stereocenters, what we can do is we can draw a plane of symmetry right down the middle of that molecule, where anything on either side is going to be identical. The same thing here. In fact, if we were to rotate along that plane of symmetry, we would get the other form. So these are examples of meso compounds, basically an achiral compound with more than one stereocenter. So how are these two related? These two are related. We keep one stereocenter the same, but we change the other one. These two will be diastereomers. Same thing in this case. We keep one stereocenter the same, but change the other one. Finally, let's take a look at these two and the relationship between these. Notice we have two stereocenters here. There's no plane of symmetry. These are mirror images of each other. These will be enantiomers. If you want, what you can do is you can double check, assign all of the stereochemistries, but in case of the meso compound, even though they will be exactly opposite, because there's this plane of symmetry, the compound itself will be achiral.